Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture we started talking about deformation behavior of composites, and we discussed about direct and indirect strengthening in the composites, right? Today we will talk about how composites behave under monotonic and fatigue loading. Okay, so let's proceed. So we'll talk about damaging particulate composite first, and then we'll come to fiber reinforced composites. Okay. So we'll first talk about how these particulate composites, MMCs, they behave under monotonic loading or say tensile testing, right? So if you do a tensile test of MMCs, particulate MMCs having different volume fraction of particulate, and if you plot true stress versus true strain, you're going to observe curve like this. So let's say we are talking about 4 volume percentage. So one is 0%, that means it is monolithic material. So unreinforced material, right? Then 10%, 20%, 30%. Okay. So you are going to observe curves. So I'm drawing rough schematic of the curves you are going to observe for these 4 composites. So these are rough schematic. Okay. So let's say now the bottom one is for 0%, then 10%, 20%, 30%. Okay. So your volume percentage is increasing in this direction. Okay. So what you observe here, that if you increase the volume percentage, so increasing the volume percentage of reinforcement, okay, you are going to observe increase in Young's modulus. Right? So you can see your Young's modulus is increasing as you move from 0 to 30 volume percentage, right? Young's modulus is stress by strain. So you can see the slope. Okay, so this particular slope here on the left side, you can see, right? So this slope is continuously increasing. Okay, and this is happening because as you increase the volume percentage, you are able to transfer more load to the harder and stiffer particulates, right? So you can, at a constant strain, you can have higher load. That means higher stress value. Okay, because of more transfer of load towards the particles. Okay? So this is happening due to higher load transfer. Remember, so this can be example of say aluminum silicon carbide composite, MMCs. Right? So silicon carbide is much stiffer than aluminum, And if you increase the volume percentage, you are able to transfer more load towards silicon carbide. That means you are going to increase the Young's modulus of the overall composite. Okay, so that is point number one. Second, you are going to see increasing yield strength. You can clearly see here, right? So your yield strength, you can see it is also increasing as you increase the volume percentage. Okay, and why this is happening? Because of the contribution from indirect strengthening. Okay, so if you increase the volume percentage, we have already discussed the contribution of indirect strengthening increases, right? And if the contribution of indirect strengthening increases, the yield strength is also going to increase, and that is what you observe in this schematic in the left side. Okay, so this is how your composite is going to behave. Overall, if you see, the stiffness is higher for MMC than its monolithic counterpart, right? Young's modulus is higher, right? Similarly, yield strength is also higher for composite than its monolithic part. That is also one of the observations you can make. Second, increasing the volume percentage in MMC is also going to increase the Young's modulus as well as yield point. Okay. Now, if you have the composites but different size of the particles, so what type of curve we are going to observe? So in the previous one, we varied the volume fraction, we kept the size constant. Now we are varying the particle size. And then we are doing tensile test. Okay. So this is a monolithic one. So 0%, right? So this is monolithic. Now we have the composites, same volume fraction but different size. So if I have 5 micron, then it is going to be something like this. I have 10 micron. It is going to be something like this. Now if I have, say, 25 micron or 30 micron, you're going to observe a different trend. Now it depends upon the processing condition. What I'm drawing here is for extruded one. So we have extruded composite. Okay. So this is, say, 25 micron. And this is 5 micron and then 10 micron. Okay. So let's say we have aluminum silicon carbide, again MMCs. And what we are doing, we have extruded it. Okay, and this is for extrusion. So it depends upon the processing conditions also. Okay, this one is for extruded one. Okay, so what are the observations you are seeing here? That if you decrease the particle size, you are going to increase the modulus as well as yield point. See, the slope of 5 micron curve is higher than 10 micron curve. Similarly, the yield point is higher for 5 micron than 10 point. That is point number one. Okay. So typically, decreasing particle size would increase the strength of indirect strengthening. Okay. So in the previous case, volume fraction was increasing, so there was increased strength of indirect strengthening. Here we are decreasing the size of the particle. That means you are creating more surface area, right? So that will also increase the magnitude of indirect strengthening. Go through the previous lecture. We have already discussed that. So this will lead to the increasing tilt point, right? That is point number 1. Okay. So that is how we go from uh, 5 micron and 10 micron. That is what we this point is about. Now the second one, if you go to very high particle size like 25 micron and above, 30 micron, 40 micron, since this is extruded particle, there are chances that you are going to have crack in those particles, right? And that will contribute towards the decrease in the strength of the composite as compared to 5 micron and 10 micron particles. Okay. So, however, if the particle size is high, so in this case 25 micron, then probability of finding fractured particles would be higher. Okay. So since this is extruded case, you have already fractured those large particles, and that is contributing towards the decrease in strength as you increase the particles, say beyond 25 micron in this case. So it completely depends upon the processing conditions. Okay. So here on the top one, contributing towards ill point. Or yield strength. Okay, so this is how you see damage in, or this is how your composite is going to behave in monotonic loading. Okay, so now this damage can occur either by particle fracture or by debonding. And this is what we had also discussed, if you remember, when we are talking about dimple formation, right? Ductile fracture. There we are talking about second phase particles, and we discussed that those second phase particles present in the commercial metals and alloys can actually fracture or debonding can take place. The same phenomena is going to observe in MMCs, right? So either by the fracture of the particles or debonding of the interface. Of particle and matrix. Okay, so if you have composite and say we have particles, so these are your particulate, right? And the white region in that rectangle is the matrix. Okay, so these are your particles. And then you are having load. So there are two scenarios. So in condition 1, what you are going to observe is the say fracture of particles. So these particles are going to fracture. Say this has fractured. Now this has fractured. This has fractured. Okay. And second scenario can be where there is a debonding of the interface. So these are your particles, and then what you see is debonding of the interface. Okay, so say this has debonded, and this surface has debonded, and this surface has debonded. Okay, and finally, if you just draw the schematic for fracture, right? Eventually, it is going to fail both of them. So you are going to observe. Now I'm drawing only two particles. Okay. In this case also, let me draw only two of them. So it is going to fail. Say something like this. Okay. So here, failure. Similarly, debonding will take place. So it is going to fail, say something like this. Okay. So the first case here is particle fracture. Second one is debonding. Okay. And then in the first case, if you again remember what we had discussed during the formation of voids, this can happen, particle fracture, when the strength of the particle is less than the strength of the interface. And the second one will be when strength of the particle is higher than the strength of the interface. Where sigma PF is the strength of the particle and sigma interface is the strength of the interface between the particle and the matrix. Okay. So overall, depending upon the interfacial strength, which is sigma interface, okay, and second one is particle strength, which is sigma PF. Okay, so if sigma PF is greater than sigma interface, then what you observe is decohesion or debonding of the interface. And if sigma PF is less than sigma interface, then you see fracture of the particle. Okay. So when you do tensile test, you can see either fracture of the particle and debonding of the interface depending upon the interfacial strength and particle strength. Okay. So this is how your composites behave under mono tonic loading, and we have discussed about the particulate MMCs. Okay, now let's discuss about the behavior of particulate MMCs under fatigue loading. So fatiguing particulate MMCs. So we'll first talk about SN curve. And when we talk about SN curve, it is for unnotched specimen, right? Okay. So in composites, most of the load is carried by high modulus and higher strength particles. Okay, so if you have the composite particulate MMCs, so most of the load will be carried by the higher modulus and higher strength particles. That much we know. And when this happens, this will lead to lower average strain of the composite as compared to the unreinforced alloy, okay, or monolithic counterpart. So composite undergoes a lower average strain than unreinforced alloy. Okay, because we have added particles in the composite which are harder as well as stiffer. Okay, so overall the composite is going to observe lower average strain in fatigue loading as compared to the monolithic counterpart, that is 0.1. Second, now if you increase the volume fraction of the particulate, right, you are going to again see the lower average strain, right? So increasing the volume fraction of reinforcement, which is particulate in this case, right, is expected to increase the number of cycles to failure. Okay, so if I now plot based on the discussion, and what do we plot? SN curve. So you have S on the x-axis, so that is stress amplitude, and then NF, right, number of cycles to failure. Okay, so if I just plot it, it will look something like this. Again, a schematic. So this way you are increasing the volume fraction. Okay, so this, the bottom one is say 0%, then 10%, 20%, and 30%. Okay, and this is the plot is for effect of volume fraction at constant particle size. Right? So even in fatigue loading, particulate MMCs are going to behave better than the monolithic counterpart. That is point one. Second, increasing the volume fraction is expected to increase the number of cycles to failure. Right? So if you increase the volume percentage, it is better in fatigue loading as well. We have observed this happening in monotonic loading. Okay. Now, if you do the same experiment for fatigue testing for constant volume fraction and different size of the particles, right? So stress amplitude, then NF. Okay. So we have first for unreinforced, then we have some composite which is named as say F600, then F1000, and the last one is say for F280, and this is unreinforced. Okay, you're going to observe the same phenomena what we discussed in monotonic loading. So here the size of the particle, if you see, so F1000 is the lowest, then F600, and then F280. So this is particle size trend. So the lowest is for F1000 and the highest is for F280, right? So if you decrease the particle size, you are going to improve the fatigue behavior. Okay, you can see here that F1000 has higher number of cycles to failure as compared to F600, right? That is point number one. Second, the MMCs are going to behave better as compared to unreinforced alloy, right? You can clearly see here. Okay. However, you have to know that if you increase the particle size beyond certain limit, then your fatigue property is going to deteriorate, right? And you can see the F280, right? You have much less number of cycles to failure as compared to unreinforced as well as F1000 and F600 composites. Okay, and you can apply the same concept what we discussed before, that this F280 composites are going to have particles which are larger in size. And remember, this is again the case of extruded MMCs. That means these larger size particles are expected to fracture before you test it, right? So obviously it is going to fail earlier. Okay. So this is the effect of particle size at constant volume fraction of particles. Okay. Again, remember this trend is for the extruded one and it can vary depending upon the processing condition. Okay. But overall, if your particle size is small, then the MMCs are going to behave better both in monotonic loading as well as fatigue loading. Okay. So this is what we discussed about the Ascent curve. Now let's talk about the fatigue crack growth. So fatigue crack propagation. Okay. fatigue crack growth in particulate reinforced composites. So now we already have a crack. We are trying to understand how this crack is propagating in particulate reinforced composites. Okay. So typically delta KTH, and what is delta KTH? That is threshold stress intensity factor range, right? So this delta KTH is higher and crack growth rate is lower in case of composites. Than monolithic counterpart or unreinforced alloy. Okay. Monolithic counterpart. Okay. So we have discussed in the SN curve that composite is better than the monolithic counterpart, especially for smaller particle size, right? So same thing here. When you talk about fatigue crack growth, the delta KTH is going to be higher. Okay. So your curve is going to move on towards right side, right? And your crack growth rate is also going to be lower as compared to the monolithic counterpart. That is point one. Second, as volume percentage of particles increases, threshold or delta KTH also increases, and crack growth rate, what is going to happen? It is going to decrease. Okay. So if you increase the volume percentage, your fatigue properties are going to improve. Okay. So if I draw fatigue crack propagation curve, and what do we have on the y-axis? dA by dN, and x-axis delta K, right? So let me draw for the first point. So we are comparing the crack growth rate behavior for monolithic and MMCs, right? So it is going to look something like this. So this one is for MMCs, and this one is for monolithic. Okay, now second plot is for different volume percentage. So one is for say 20% and another one is for 30%. So 30% right one, 20% left one. dA by dN versus delta K. Now what is delta KTH? So for monolithic, this is your delta KTH. And for MMCs, delta KTH is. So let me write down delta KTH1, which is monolithic, delta KTH is 2 for MMC. So you can see delta KTH for MMC is greater than delta KTH1. Similarly, for same delta K value, you can see the monolithic has higher crack growth rate as compared to MMC, right? So if I just draw say a straight line, same delta K, you can see that dA by dN is higher for monolithic, right? And that is what it is written, the first point. Now, second one, if you increase the volume percentage, threshold increases, right? So here say this is delta KTH2 corresponding to 30%, and this value is delta KTH1 corresponding to 20%. So there is an increase. If you increase from 20 to 30, now again for same delta K, you can see that for 30 percentage, dA by dN is lower than the 20%. So overall MMCs are going to be better, right, in fatigue crack growth behavior also. Okay. Now why this is happening? If you see delta KTH is going to be higher, right, in MMCs. And if you see the top part here, you can see that it is going towards the monolithic if you increase the delta K. So at lower delta K, you have much improvement in the fatigue behavior of MMCs, but at higher delta K, it is going towards monolithic, right? So what is happening? So at lower delta K, that is say near threshold, cracks will tend to, and we will discuss about this concept in a bit, will tend to bypass the particles. Okay, and this will lead to rough crack surface. Okay, and this will happen due to crack deflection and meandering or meandering. Okay, so what I'm trying to explain here, that delta K is lower, right? So the crack is going to bypass the particle rather than fracturing the particle because delta K is lower, right? And we'll discuss this concept in a bit, but let me draw, say, two particles. Okay, so if you have a crack, it is going to bypass it. Say something like this. Okay, so bypassing. And this is your crack. Okay, and when it bypass, what you see is the crack deflection and meandering, right? So it is going to decrease the crack growth rate, isn't it? Because the crack now length becomes much larger. Okay, so when this happens, this lead to decreasing crack growth rate as well as higher delta T. Okay, and if you increase now the volume percentage, what is going to happen? You are going to observe more crack deflection, right? That will lead to lower crack growth rate and increase delta K TH here, not delta K, right? Okay, higher delta K TH. Okay, so if you have monolithic, then you are not going to observe this crack deflection and meandering, right? So you are going to have higher crack growth rate as well as lower delta KTH. But in the MMCs, because of the deflection, you are going to observe lower crack growth rate and higher delta KTH, and the strength of this is going to increase as you increase the volume percentage of particles, right? Now, if you go to higher delta K, you are going to see the fracture of the particles. right? And that means you are going to observe planar sort of crack because there is no deflection. Particles have already fractured. Now crack will prefer to pass through those fractured particles because then crack is going to spend less energy. Okay, so you're not going to observe the deflection. That means your crack growth rate is going to increase, right? So at higher delta K, particles can fracture ahead of the crack tip. And when this happens, you are going to see easier crack growth. Right? Crack will pass now through the already fractured particles. And this will lead to higher crack growth rate. And what you observe is more or less flat crack path, or say less deflection, or more or less no deflection. Okay. So here at low delta T, at low delta K here, right? You observe crack deflection. At higher delta K in this regime, you are going to observe, say, particle fracture. So if crack growth rate increases, it can go to near monolithic material or monolithic alloy. Okay. Now let's understand how it is going to behave at different R ratio. We have discussed the concept of R ratio, right? It is the sigma minimum by sigma maximum, or K minimum by K maximum, or P minimum by P maximum, depending upon the configuration. You can calculate what is K minimum and K maximum also, right? So depending upon the R ratio, you are going to see that the composites are going to behave differently during fatigue loading. Okay. So here what I'm showing that we have two R ratios, R equal to 0.6 and R equal to 0.1. Here. Okay. And I have the table which shows some calculations. You are doing a fatigue test on, say, SENT specimen. I've shown at the bottom. Okay, specimen dimensions are very small, 12.74, etc. Okay, B is your thickness. Okay, height is 12. Anyway, so for delta K of 6 MPa root meter, we can note down the load requirement on the right side. If you see, it is 353 is the maximum load and 215 is the minimum load. Okay, now if I keep every value same in the above table and just change the value from R equal to 0.6 to R equal to 0.1, delta K is going to be very high. It is going to be in the range of 13.50 MPa root meter. Okay. See, load is same, 358.3 and 35. And then because it is R ratio is 0.1, obviously the minimum load is going to be different, but maximum load remains same. Right? So delta K is going to be high, 13.50. Now, if I want to compare what is happening at the same delta K, right? Right? What is the crack growth rate or how crack is propagating at the same delta K? That is what we have done in the third table here. So now delta K we are maintaining at 6 MPa root meter as we have in the first table for R equal to 0.6. So what we have to do, we have to change Pmax. So now the Pmax is 143.3 Newton. Okay. And delta K is nearly 0.1. nearly 6 MPa root meter. Okay, so it is nearby now. So in table 1, which is R equal to 0.6, delta K is 6, and in table 3, delta K is 5.4. So which is nearby. Now we can compare what is happening between table 1 and table 2. Okay, that is different R ratios, but delta K remains same. Okay, delta K is your driving force in fatigue. Okay, so now for same delta K, in low R ratio, Kmax is very small, right? Because Pmax is small. If you see, Pmax is 143.3. But at high R ratio, your Pmax is 358.3. See the table 1, right side. That means Kmax is going to be very, very high, right? So low R ratio, your Kmax is low, and high R ratio, your Kmax is going to be high. And if that happens, what will be the result? So the effect of Kmax, you're going to see higher plastic zone size, right? Because Kmax is higher at higher R ratio. In this case, R is equal to 0.6. Okay, so you are going to observe higher plastic zone size as R equal to 0.6. Now, if you have higher plastic zone size, the particles in those plastic zone can fracture ahead of the crack tip. So, if you have a crack and if you have these particles which are in the plastic zone size, these particles can fracture, right? And this fracturing of the particles is going to observe predominantly in high R ratio, right? In low R ratio, your Kmax is going to be lower. That means particles are not going to get fractured ahead of the crack tip. That means you are going to see crack deflection rather than particle fracture, okay, or crack passing through the particles. So two things are there. At low R, at high R ratio, the particles are going to fracture ahead of the crack tip, and then crack is going to pass through those fractured particles. That is point number 1. Second, at low R ratio, since Kmax is small, your particles ahead of the crack tip cannot fracture, right? Instead, the track is going to bypass through those particles, right? That means you are going to see more deflection of the track. That is what I have written at the bottom here. Okay. So if you have a track at high R ratio, you have particles. So these particles are going to get fractured. Okay. And at low R ratio, in front of the track, you have, say, these particles. So your track is going to bypass. So it is going to behave something like this. Okay. So here predominantly particle fracture, and here crack deflection or bypassing the particles. Okay. At high R ratio, after the particles have fractured, this crack is actually going through these fractured particles. Okay. And since volume percentage is sufficient, you are going to observe more or less flat. Okay. So this red line here is crack. Okay. So this is how your composite is going to behave at high R ratio and low R ratio. So overall, what you observe is for both R ratios, as Kmax increases the number of fractured particles ahead of the crack tip also increases. See here, Kmax is dominant, right? At high R ratio, your Kmax is already higher. At low R ratio, your Kmax is lower. But if you increase the crack length, see you're doing fatigue, so crack length is going to increase. So after certain amount of number of cycle, your crack length has increased sufficiently that at low R ratio also, because of the increase in crack length, your Kmax is also higher, right? So after certain point, what you are going to observe in low R ratio, that the magnitude of particle fracture is also going to increase. Okay. So when you start the test, your crack length is lower. So at low R ratio, your Kmax is low. So you are not going to observe particle fracture. But with increase in the crack length, you are going to increase the Kmax and you are going to observe the particle fracture also in low R ratio. In high R ratio, whether it is small length or larger length, you are predominantly going to observe particle fracture ahead of the crack tip. And then the crack is going to propagate through those fractured particles because of spending of less energy. Okay. So if I now plot, say, number of particles versus Kmax. So, increasing the Kmax is going to say increase number of particles. I'm just drawing some rough data. So this could be for your low R ratio. And this higher region is for high R ratio. So overall, high R ratio will always lead to the higher number of fractured particle as compared to low R ratio. That is point number one. Second, even in low R ratio, your number of particles fractured is going to increase as Kmax is going to increase, right? So during fatigue, if A is increasing, Kmax is increasing, and you are going to increase the number of fractured particles even in low R ratio. Okay, so it depends predominantly Kmax, right? What is the value of Kmax? So this is what I wanted to discuss about the particulate reinforced metal matrix composites. Now let's talk about fiber reinforced composites. Okay. We'll talk about monotonic loading of fiber reinforced composite. So monotonic loading of, we will talk about continuous fiber reinforced MMCs. Okay, now it depends upon three factors mainly. So first one is your obviously fiber characteristics. The second is nature of interface. And the third is matrix characteristic. Okay, so it depends upon the volume fraction of the fibers, nature of the fiber, etc. Second, which is the important one, is the nature of the interface, and we'll talk predominantly about nature of interface, how it affects the monotonic behavior of continuous fiber reinforced MMCs. Okay, so let's see what happens when you have a composite and you have fractured one of the fibers. Okay, so damage in the composite when a single fiber is broken. Okay, so you can have two cases. Let me first draw the schematic of composite. So see, you have fibers, this blue one. So this is the schematic, okay? So these are fibers. Okay. And then you have loading. So two scenarios can happen. So the first one is for weak interface. And the second one is for strong interface. And this one is called global load sharing. And the other one is local load sharing. Okay, so the first one is weak interface. What does it mean? That suppose you have fractured the fiber. Let's say this fiber is fractured here. Okay, and here also let's say this fiber is fractured. Okay, the purple one. So as soon as in the weak interface the fiber is fractured, you are going to see debonding because your interface is weak. So you are going to see debonding of the interface, right? In the fiber, second case where the interface is strong, as soon as your fiber is fractured, you are going to see continuous fracture of other fibers and more or less a flat failure you are going to observe, right? So it is proplanar failure. And here what you are going to observe is matrix sharing or fiber debonding because interface is weak, right? So once the fiber is fractured in the first case, you are going to see the debonding, okay, of the uh, matrix or of the interface between the matrix and the fiber, right? And these local energy absorbing mechanisms, they will allow for the redistribution of the load, which was originally borne by that particular fiber. So let's say this fiber I give number 1. Okay, so originally this fiber was having contributing or having some load, right? Now this load will be redistributed because this fiber has fractured, and this load will be redistributed towards the surrounding fibers, right? And that is why this is called global load sharing. All the fibers are sharing the load. Okay. Now, in the second case, there is no deflection or debonding of the crack because your fiber, your interface is not weak, it is strong. So once one of the fiber has broken, the load cannot be distributed homogeneously. So once one of the fiber is broken, it will result in the continuous fracture of adjacent fibers. And so let's say number one, this is number one. So once this number one fiber is fractured, number two, number three, number four, all these fibers continuously fracture, leading to the failure of the composites. Okay, and this is happening because of the localization of the strain around a single fiber, right? And that's why this is called local load sharing. So in monotonic loading, you can have either global load sharing or local load sharing depending upon the nature of the interface. If interface is weak, it will lead to the global load sharing, and if interface is strong, it will lead to the local load sharing. Okay. Now, how do we improve the toughness of the composites, right? So this is what I wanted to explain. So toughness in fiber reinforced composites, right? And if we want to increase the toughness, we have to somehow spend energy, right? The more you spend energy in the composites, the more tougher the composite is, right? So let's see how it is being affected. So first is your matrix deformation. So this is very important when you have ductile matrix. For ceramic matrix composite, this is not important because the matrix is ceramic and it cannot deform very nicely, right? But if it is a ductile matrix, then yes, you can spend some amount of energy which will lead to an enhanced toughness. Okay, that is point number one. Second, fiber fracture. So when you have fibers, these fibers can fracture, and that will also lead to the enhancement in the toughness, because you're going to spend some of the energy when you fracture the fibers, right? So metallic and polymeric fiber contribute towards the plastic deformation, but ceramic fibers, they do not, right? And I will show you later that fiber fracture need not occur in the crack plane. It can happen away from the crack plane also. That is point number two, fiber fracture. Third, interfacial debonding and crack deflation. And this is very, very important. And this happens especially when you have weak interface. So if you have a crack, it is propagating, and as soon as it sees an interface which is weak, you are going to observe interfacial debonding first, and then crack will be deflected at the interface. And when this happens, you are going to spend some energy in the debonding as well as deflection of the crack. That means you are going to enhance the toughness of the composite. You are going to consume some energy, okay, by debonding and crack deflection. Now the last one is fiber pull out. Once the fiber has fractured, you have to pull out the fibers. They will be separated and they will be pulling out of the fibers. And this pulling out of the fibers will also require some amount of energy. That means it will also contribute towards the toughness. Again, you will see that fiber fracture can happen away from the crack plane. Okay, so these are the some ways where we are going to spend energy in fiber reinforced composites, and all these factors are going to contribute towards the toughness of fiber reinforced composites. Okay, so now let's talk about the enhancement in the toughness, especially in ceramics matrix composite, because the matrix itself is ceramics, right? So how do you enhance the toughness? And what is the way of having some toughness in ceramics matrix composite, because the matrix itself is ceramics. Okay. So ceramics matrix composite. So you could have two cases. Case one, if the interface is strong. Okay. So if interface is strong, I have mentioned that you are not going to see debonding, rather you are going to observe fracture of the fibers. So fibers will break. Okay. And then you are going to see brittle nature of the composite, because once the fibers have broken, matrix itself is ceramic, so crack will just propagate like that, right? So brittle nature of composites. So fracture in a single plane, right? So if you have a composite and the interface is strong, so let's say you have a fiber. So these are your fibers. Okay. So let's say two fibers here. So if the interface is strong, so what is going to happen? Your fiber will break, right? So suppose a crack is coming. So your fiber will break here. Your fiber will also, this crack will just join, and then this is ceramic. So as soon as it comes here, the fiber breaks again. So what you see is your planar crack. Okay. So this will happen when your interface is strong. Now case two is if the interface is weak. Now here we are going to see lots of phenomena happening in fiber reinforced composite, which will lead to an enhanced toughness. Okay, so the first is debonding. Second, crack deflection. Third, crack breaching. I will explain all of them. Okay, so this is number one, number two, number three. Number four is fiber fracture. And after fracture, you are going to have fiber pull out. So let me explain this phenomena. So you have a crack. Okay. And then say you have fiber here. So this is a fiber in the composite. And crack is approaching towards the fiber. Right? We know now in front of the crack tip, we are going to have higher stress concentration. Okay. And if the interface is weak, you are going to see debonding of the interface. Right? So this is the debonding of the interface. Ahead of the crack tip. Okay, this is fiber, and say this is the crack. So crack is approaching towards the fiber and it sees a weak interface, right? So that interface is debonded now. as soon as it has debonded, this track is going to get deflected. So something like this. And then you have the fiber. So you see the track is not deflected 90 degrees. Okay, so track direction is like this, but it has not deflected by 90 degrees. So what you observe here is track deflection. Track deflection due to debonding. So first debonding has occurred. As soon as now track reaches towards the debonding region, you are going to see the track deflection. It has not deflected by 90 degrees. And remember, in all these processes, you are going to absorb or consume some amount of energy, and thereby you are enhancing the toughness of the composite, right? Now this process will continue. So now the track is propagating away from the fiber, right? There is a track deflection. Now, if you have this fiber, the track has come here, it has not deflected. So now the track has moved, it has surpassed the one fiber. It will go to the another fiber. In the second fiber also, you're going to see debonding and the track deflection, and the process will continue, right? So what you are going to observe finally is that you have a track, and in between the track, you are going to see all these fibers, right? So these fibers are actually breathing your track, isn't it? And that is what we call as track breathing. Okay. And when that happens, that will also enhance your fracture toughness. So let me draw the schematic. So the third is you have this track, and then say you have all these fibers. Something like this. Okay. So these are your fibers. And then this is your track. So track is going from the fibers, right? So if you see, this is your track area. Okay. So you have fiber and track is passing through that fiber. Fiber has not fractured. Okay. So what you see is the breathing of the track because of the presence of fibers, right? So fiber has not fractured. So here what you see is track breathing. Now this will enhance the fracture toughness also, right? Remember, when track breathing is occurring and say we are applying load, right? Now, if you remember the stress concentration concept, if you now start drawing the stress trajectory, right? In front of the track tip, assume that these fibers are not there, right? So in front of the track tip, you're going to have certain stress concentration, correct? Now these fibers which are bridging the track, they are also going to take some load, isn't it? Some of the stress trajectory or line of forces are going to pass through these fibers also, right? So the number of these stress trajectories in front of the crack tip will be much lower when you have crack breathing as compared to when you don't have crack breathing, right? Or fibers have say fracture. So suppose there is no fiber. So now let me explain it in a better way. Suppose you have a track, there is no fiber. So if you remember the stress trajectory concept, we discussed something like this. So you are going to have certain number of line of forces, imaginary line of, and this is the concept of stress concentration in front of the crack tip, right? Now, if I just put fibers here, now some of the line of forces will pass through these fibers, right? Because this fiber can take the load. Previously it was air. Now these fibers can take the load. So some of the stress trajectory will pass through it. That means you are going to lower the stress concentration in front of the crack tip in the presence of fiber bridging when you have fibers. Okay. That means the stress concentration factor is lower, right? That means the crack propagation rate is also going to be lower. Now, if somehow these fibers are fractured, suppose I fracture these fibers. Now, the situation is similar to the case when you don't have fibers, because when the fiber has fractured, it cannot take any load. Okay, so this is how you understand the concept of crack bridging enhancing the toughness of the composite. Okay, now, so this is step number 3, where you see crack bridging. Now, the next step is you are going to observe fiber fracture. Okay, and I forgot to mention here you are going to see deflection and debonding. We are talking about weak interface, right? And that's why you see crack bridging. Otherwise, you will see the fiber of the fracture of the fibers. Okay, so now we will have fiber fracture. Let me draw the fibers. So these are the fibers in the composite, and then you are going to observe fracture. So here you have, say, debonding. And then you're going to observe fracture of the fiber, say something like this. In these regions, they have fracture. Okay, and you have crack here already. So this is your crack. Okay, so these 1, 2, and 3 fiber fracture. So after crack bridging, now this fiber is going to take load. Eventually, these fibers are also going to fracture. And when that happens, your whole composite is going to fail. So this is how it happens, right? It starts with the debonding, then crack deflection, then crack brazing, and finally you're going to have fibers which are taking this load. So fiber fracture is going to occur, and finally you're going to fail the composites. Now you see the fiber fracture can take place away from the crack plane also. So this is your crack plane. Right, so this is your crack plane, but you can see the fiber fracture is occurring away from the crack plane also. It is possible when you have the weak interface. In a strong interface case, the crack plane will be your fiber fracture plane also. Okay, so this is the difference between the weak interface behavior as compared to the strong interface behavior. Okay. So now let me show you some of the images. So the first one is for monolithic ceramic versus fiber reinforced CMCs. And then I will also show you the schematic of steps in the weak interface. Okay, and some SEM images of fiber pullout. So this is the paper by Kim, okay, in Materials 2020. This is the title of the paper. So this is the fracture behavior of monolithic ceramics and ceramic composite, right? So if you see the red one here, this is the ceramic, monolithic ceramic, right? So if you just do the tensile testing, you are going to observe brittle failure, that you know. What you see in the red, black one is the ceramics composite, right? So if it is strong interfacial bonding, you see this particular line here. So this is going to be also brittle. So it will go like this and then it will fail. Okay. But if it is weak interfacial, it is going to absorb more amount of energy because of the phenomena we have discussed, right? Debonding, crack deflection, crack brazing, fiber fracture, and fiber pull out. Okay. And that is what you observe this whole curve here, right? This is because of all these phenomena happening. Okay. And this is the schematic. If you see, so you have the crack, right? And you can see debonding here. Okay. And then you can see crack bridging. So this is what I meant by crack bridging. You have this crack and then these two fibers, the second and third fiber, they are bridging the crack. The first one is the crack, the fiber is already fractured, right? The second and third is crack bridging. They are showing the crack bridging phenomena. Okay. Here you can see fiber pull out. So these are your fibers. Okay. You can clearly see pull out of the fibers. Okay. So this is one. Second is fiber pull out and fracture. Let us see. So this is in composite part A, applied science and manufacturing, 2021 by Liu. See, these are your fibers, huh? You can see. Okay. So you can nicely see here fiber pull out. Okay, so see, this is the hole. So fiber has been just pulled out. So on the other side, you're going to see just the hole, because on the other side of the fractured sample, you're going to see fibers. So you can see these fibers are coming out, right? So one side you are going to, so you have two surfaces, right? Fracture surface. So in one side of the fracture surfaces, you are going to see fibers are coming out, right? In another side, you are going to see hole, which will correspond to the each fiber, which you observed on the other side of the fractured surface, right? And these area, if you see, this is happening because of the interfacial bonding, strong interfacial bonding. So what you see is the fiber fractured, but you don't see it pulling out, right? It is on the same level as the fracture surface. You can see here. So this is your fracture surface, right? So it is on the same level of the fracture surface. So this is a typical example of when you have strong interfacial bonding. And if you see feeder B, this is coming out. So your fracture surface is at the bottom and then your fiber is on the top of it. So this is the example of fiber pull out. Okay. And if this is your case, see this finger is my fiber and this is your fracture surface. So this is the case of strong interface and this is the case of weak interface when your fiber is coming out of the fracture surface. Okay. I have another example. So this is how your fibers look like. Okay. Here. See, fibers are out from the fracture surface. So these are your fiber pull out. If you see the other surface, you will see the hole, which will correspond to each fiber. Okay, you can see here also lots of fiber pull out. Okay, and doing that, you are going to spend lots of energy. Now let's see particle fracture and debonding we discussed. So this is the paper by Professor Chawla. The fracture toughness and fatigue behavior of DRA by Pandey and Professor N. Chawla. So this is your MMC, right? Particulate MMC. So this is 7093 silicon carbide composite. Okay. So see here, you have two fracture surfaces. So after it has fractured in monotonic cladding, you see one part, another part, and this A will correspond to another A here on the other fracture surface. So each particle is separated into two parts. One will go to one fracture surface, another will go to another fracture surface. So this is a typical case of particle fracture. So once a particle has fractured, right, One part will go to one fracture surface and another part will go to the another fracture surface. That is what you observe in these two images. Okay, so this A belongs to this A. Similarly, this B belongs to this B. Okay, so this is a case of particle fracture. Here, in this case, what you see is the particle debonding. So this is A is one fracture surface and a B is the other part of the failed part, right? So here you can see the particle, but on the other side, you don't see that particle, the same particle, right? That means particle has debonded. So only on the one fracture surface, you are going to observe the particle, and another fracture surface, you are going to see hole corresponding to that particular particle. Okay, so this is how you see particle fracture and particle debonding. Okay, and last one is the fatigue crack growth at low and high R ratio, and I am one of the co-authors, and this was by Peter Ruby in International Journal of Fatigue. You can see Sudhanshu S. Singh here. So let me show you quickly the experiment. So this is the loading gauge and this is the small sample we used, and data I had shown you before, right? And this is the composite. So you can see these are your particles, and this line you see, this is your crack. Okay, you can see the crack tip. So, okay, so if you see, this is at high R ratio, right? So your crack is here. If you see this particular particle, this gets fractured ahead of the crack tip. And after it has fractured, this crack is actually passing through this fractured particle because now it is spending less amount of energy. Okay, and if you see here R equal to 0.1, you see not the particle fracture but debonding, right? So more crack deflection. Okay, and then we quantified also the number of particles with respect to crack length. As crack length is increasing, Kmax is increasing, the number of particle is also going to increasing, right? And number of particle is going to be higher at R equal to 0.6 as compared to R equal to 0.1. That is what we discussed. Okay, and this is the plot I was talking about, the number of particle fracture per unit crack length. And if you plot with respect to Kmax at R equal to 0.1, which is the red one, and R equal to 0.6, which is the blue one, you see that at high R ratio, your Kmax is going to be always higher than R equal to at low R ratio, which is R equal to 0.1. So number of particles fractured is always going to be higher at R equal to 0.6. And as you increase the crack length, Kmax is going to increase in R equal to 0.1. So number of particles is also going to be slightly higher, okay, as you increase the Kmax. Okay, so this is what I wanted to discuss about the deformation behavior of composites. So we started with direct indirect strengthening, then I discussed about the monotonic as well as fatigue behavior of particulate reinforced composites, and then we discussed about the monotonic behavior of fiber reinforced composites. Okay, so I will stop here and we will meet in the next lecture. Thank you.